Everyone, I've been exploring voice AI agent and came across Pipecat and I thought I will share my learnings with you regarding Pipecat and voice AI. So let's get right into it. So uh, I've created this presentation using AI and I'm gonna share my learnings regarding Pipecat voice AI, whatever I have learned, and also I'm gonna walk you through one of the example related to the quick start of the Pipecat. So there was some few uh, theoretical concept that I thought I will be sharing with you to help you understand and get started with Pipecat. So let's get right into it. So let me start it. Okay, so first of all, goal of this presentation is not about API or Insta. It is about understanding how real-time voice AI actually works. And if you understand the mental models, the code becomes obvious. So by the end, you should be able to read a Pipecat bot and know why each part exists, and also reason about latency, interruptions, and architecture. So first of all, what is voice AI agent? Voice AI agent is not just speech in, speech out. It must listen continuously, not in chunks, and it must think while it's listening. So it must speak while being interruptible. So human interrupt each other naturally. The AI should also allow it. So it is actually very different from record, upload, wait, and reply system. So voice AI must feel like a phone call, not a chatbot. So if your system feels like talk, wait, response, like that's chatbot, not a voice AI agent. So why real time is non-negotiable? Because human conversation is fast and overlapping. Silence of longer than 500 millisecond feels awkward. So we expect our voice AI agents to also be something around that latency. So if it is more than that, then conversation feels broken. So human expect back channels like those kind of sounds, interruptions, natural pacing, and HTTP request response breaks this model. So that's why uploading audio files does not work. Streaming is kind of mandatory for voice AI agents, and that's why WebRTC came into the picture. So WebRTC is a technology about real-time media, not AI. So WebRTC and AI are two different things. It's about real-time media, and it handles a lot of things like net traversal, encryption, live audio streams, and aiortc is kind of a library for Python. So it's a WebRTC library for Python, and it handles all the networking and net traversal, firewalls, and everything. And it is used to send and receive live audio, and it does not do anything related to AI or STT or TTS. STT is speech to text or text to speech. So you can think of aiortc as a real-time audio cable between user and Python. And here is a small mental code, like we have using this we create the peer connection, and then we track like add audio track. So yeah, so only thing to note over here is like WebRTC, like aiortc just moves audio. And coming to Pipecat, so Pipecat lives above WebRTC. Like Pipecat answers the questions like what do we do with audio, when should we think, when should we speak. Pipecat does not handle networking or replace AI vendors. Pipecat is like the orchestration. So if you want to think of a mental model, then WebRTC is like ears and mouth. Like this WebRTC is ear and mouth, and Pipecat is brain and nervous system. So here is a high level architecture. So like we have the user on a browser, and this is the Pipecat pipeline. So WebRTC is used to carry that audio to the Pipecat pipeline, and then once the synthesized voice is created, it is WebRTC is used to take it to the back to the user. So this is the whole high level architecture, and there are two pieces involved. One is the transport layer, which is done by the aiortc library, and the other is the pipecat pipeline, which decide what to do with the audio. So these are two different things. So pipecat pipeline decides what to do with the audio, and WebRTC or aiortc takes the audio and takes the audio back to the user. So this transport layer moves the audio, and pipecat pipeline decides what to do with the audio. And WebRTC is kind of like you can think of it as a ear and mouth. It is listening and it is then taking back to the user mouth, and pipecat is the brain and nervous system of this. So this separation allows like a replaceable transport and replaceable AI providers, and keep those two separate. So the same pipeline can work with browser, phone call, mobile app. Now coming to the pipecat uh, pipe like pipecat frames. So everything in the pipecat pipeline, everything in pipecat is a frame. So is it's a fundamental piece, like atomic unit in pipecat. So when we are dealing with audio samples, like we have this audio frames, and then if we are dealing with text, then that's a text frame, and then we also have a llm run frame, which we are gonna come to it, which we send as like run the llm now, and control frames to control the pipeline, like stop, interrupt, etc. So this allows streaming, partial results, and real-time control. So everything in pipecat pipeline becomes a frame, like whether it is audio, text, or control signals. So frames are what make interruption possible. Now um, coming to pipecat, like a processor is a very important part. So like in pipecat we have different kind of processors which process the frame. So like we have processors is like a single function which receives frames and does something and then emits new frame. So processor is a single step in a pipecat pipeline. So we have like a bunch of different processors, like STD processor, it takes the audio and converts into text, and similarly LLM processor, which takes the like text and then do the reasoning part and then convert that to the reasoning text, and then TTS takes those text and convert back to audio. So we have all different kind of processor. So processor is a single step in the pipecat pipeline. And why processors matter? Because they are modular and replaceable, they are very stream friendly, and they are easy to extend. So we have clear separation of concerns. So that's why we use a pipecat processors. So we'll share that in the example next. So here is one working example flow. So we have like a audio frame which is taken by STT processor that converts it into text frame. Then LLM takes that frame and then convert it into some other reasoning text, like how can I help you, and then that is taken by text to speech processor and that converts this text into the audio frame. So this is the pipeline, the whole pipeline, and each of these pieces, STT, LLM, TTS, these are the different processor. So processor is a function that reacts to incoming frames and produces the outgoing frame, often asynchronously and incrementally. So it does not handle networking, and it does not manage a WebRTC control the event loop. It is just takes one input and gives the output frame. So here is one more example via diagram. So incoming frames, processor function, outgoing frames. So this is what makes stream partial responsible, interrupt mid sentence, and cancel downstream processing. So yeah, because of these processors we can do all of these things, and processor works with frames. This is the whole concept of processor. And then coming to we have different things you will hear people talking about, which is like one is VAD, voice activity detection. So what does VAD solve? So VAD is basically it solves, is the human speaking right now? Because WAD, without WAD we wouldn't know whether the human is speaking or not, and if we keep our model always on, uh, it will incur us a lot of costs. So voice activity detection helps us solve that problem. Like it helps us know, okay, now someone is speaking, human is speaking right now, so let's activate the pipeline. So this is void is actually used for that. So it detects speech versus silence and prevents sending silence to speech to text. If it wasn't there, then we will be sending the silence data to speech to text, and then we wouldn't have anything to convert, right? So our model will be, pipeline will be running, and we will be incurring cost because of that. So it helps in reducing the cost and improves latency. It does not understand meaning, it does not decide turns, and it does not control the AI. So WED does not do any of these. WED just solves the problem of detects, like, is the human speaking right now or not. So yeah, then we have turn analyzer, and it helps us solve the, is the human done speaking or not? Because a lot of times when we are speaking with the AI, we have to understand, like AI has to understand whether the human uh, like human is done talking or not. So uh, whenever we are talking, like as I'm speaking right now, I'm taking minor pauses, right? So that's how the human generally think and speak. And 10 analyzer solves the problem, like whether the human is done fully speaking or not. And the turn analyzer waits intelligently, prevents cutting user off, and signals when a turn ends. And yeah, uh, when we are done, it emits a signal like nothing more is required, and then we can run the pipeline. So now coming to the transport, if you remember from the previous slide over here when I was talking about the transport, uh, like VAD and turn analyzer, they are part of the transport, not the pipecat pipeline. So we have this pipecat pipeline which is over here, and then aiortc, the transport which moves the audio. So this VAD and turn analyzer, these two these are part of the transport. And because it directly work on the raw audio, and we need to react in millisecond. So we need to enable in the transport, we need to understand, like when the human is speaking and when the human is done speaking, then only we will proceed with the pipeline. And in case the pipeline is running and midway human starts speaking, then we have to interrupt. So this turn taking model takes care of that. Okay, turn taking logic recognizes human is now started speaking. Let's say our pipeline is running, and it is AI is saying something, but human interrupts the AI. So now AI has to stop and listen, right? So this is done by the turn taking logic, and that's why WAD and turn taking model sits inside the transport. And then uh, once human is done talking, then it start processing and running the pipeline. And that's how we enable the interruption bargain and prevent wasted STT LLM work, TTS work. Yeah. So next, coming to the Pipecat pipeline. Pipecat pipeline takes care of all the processing, like like each it's kind of like a chain of processors. Like each processor receives frames, like we have this audio frame, then speech to text, convert that to text frame, and then LLM takes that text and converts to the another text frame, and then text frame gets converted into audio frame. So this is the typical pipeline. And each step receive frame and emits frame. This makes the system modular, replaceable, and streamable. Yeah, and this is why Pipecat scales well. This is a small example. Like we have the transport, like in the previous example, this example where I showed, like this is the transport input that we are sending into the pipeline, and this is the transport output. Pipecat pipeline receives the audio input and then gives the output. So yes, so this is the transport input, and then we have a bunch of things, and then the transport output. In between we have STT, LLM and TTS, speech to text, LLM and text to speech. So audio is given to speech to text, then text is converted to reasoning text, and then reasoning text is converted back to speech using TTS. So yeah, and RTVI, I will be coming on to that, hold on to that. But uh, just to give you a brief idea, RTVI, RTVI, this is the key point. Like RTVI controls the AI. That's why it needs to come above STT, LLM, TTS, because let's say if humans start speaking midway, we have to stop this LLM, STT, LLM, and TTS processing. So that's why RTVI comes above the STT, LLM, TTS. So we have to observe the input, control downstream behavior, and inject control frames. So we have this bunch of things related to pipeline. Uh, uh, Pipeline, we have in the example we will be seeing how we are writing the code, but this is the pipeline that we have created. Then there is pipeline task and pipeline runner. So the objective of pipeline task is like it holds the state and observes what is happening in the pipeline, and checks the metrics, and it can cancel or restart the pipeline task. uh, Pipeline runner executes those tasks, and manages async loop and shutdown. So pipeline is kind of like a blueprint of what everything we needs to be done. Pipeline task is the actual instance of the pipeline that is running, and pipeline runner is like which executes those tasks. So a mental model is pipeline is kind of a recipe, pipeline task is meal being cooked, and pipeline runner is kind of like the kitchen where the we are creating the meal. And here is a small example, like the pipeline that we have created. We give it to the pipeline task, and then pipeline runner runs that. So we are doing runner dot run the task. So this is how we create the pipeline code. This runs a live real-time voice agent. And sometimes we get confused between RTVI, VAD, and turn analyzer. So VAD and turn analyzer listen to the human, but RTVI controls the AI. So in the pipeline, in the pipeline that we have, Pipecat pipeline, we have this RTVI above STT, LLM, and TTS. Main objective is because RTVI controls the AI behavior. RTVI decides should the LLM run, should TTS stop, should we interrupt. Without RTVI, AI would keep talking. Like even human is interrupting. If RTVI is not there, it won't stop the LLM, it won't stop TTS. We need to stop all of that, and AI would keep talking. So without RTVI, AI wouldn't stop. So when the LLM should run, whether to stream partial responses and all of that. So uh, so for example, AI is speaking, and a user interrupts. So RTVI cancels the AI, and RTVI is used to interrupt that. So VAD detects the speech, turn analyze, decides analyzes whether it is um, uh, whether we are involved or not, and RTVI cancels the TTS and LLM immediately. So without RTVI, AI would keep talking and conversation would feel broken. Now in the RTVI, we have like there are something like observer in Pipecat. If you know about observers, like the main thing is to observe the pipeline. So watch what happens during the execution, and understand the details of those events. So Pipecat is like a event driven system. So we kind of get all the information of all the events. So observer listen to those events and then take some action. So we have this RTVI observer which takes care of the RTVI. I will be explaining that, but basically the thing with we have this observer which using this we can observe what's happening in the pipeline. If there is something when the turn is ending, when LLM is starting, we need to do something logs and monitoring, then using observer we can do that. And we have something like RTVI observer. So RTVI observer is kind of like when our pipeline is running, and where is that? Yeah. So when our pipeline is running, let's say, so RTVI it's interrupts the pipeline, right? But how would this RTVI know when to interrupt the pipeline? So we have this RTVI observer. It observes all the events, and once our transport sends the event using bad or turn analyzer that human has started speaking. So RTVI observer tells RTVI, okay, human has started speaking, you need to cancel the LLM processing TTS and all of that. So RTVI does not decide on its own. RTVI observer lets it know. So that's why RTVI is the brain and hands, but observer is the eyes. So eyes tell the brain, okay, this is happening, and then brains take some action. So yeah, so RTVI processor lives inside the pipeline, but RTVI observer does not live inside the pipeline. It lives inside the pipeline task, and it listens to the pipeline events and informs RTVI what actually happened. And then RTVI takes some action like cancel LLM or TTS and injects control frame, actively changes behavior. So yeah, so this is what actually happens. Uh, and Do observer get notified at every step? No. So let's say a lot of things are happening, we are processing frame by frame and everything, but observer uh, only sees the event, like when something has started, when something has ended, like those events. It does not see every audio chunk or every LLM token, only sees the events, meaningful milestone, whether something has started, whether something has stopped. So all those events it sees. So mental model is observer sees the chapter in a book, not every word. Each and every chapter in the book, it sees the headline, not all the words inside the chapter. So yeah, so then we also have something metrics, metrics like for in order to understand what's happening in the pipeline. We can have different dashboards, like metrics for latency, duration, token usage, and all of that. And it is enabled per pipeline task, like one instance of pipeline. So what's happening with that pipeline? So used for cost and performance tracking, and numbers collected per conversation. So this is what the metrics is about, and what happens when a user connects. So first time, let's say when a voice agent is connected, uh, LLM need to run and say something, right? Our voice AI should say, "Hey, what can I do for you?" Right? Whenever you are connected to any voice AI agent, or whenever you are speaking to someone, you makes a call. Someone has to say something. Hello, hey, right? So something, this is something that we have to trigger manually. So we have some event related to that. So whenever the connection is made, whenever client is connected, then then we send an event, LLM run frame, and that makes the LLM say something like you LLM, and then it is sent to text to speech, which makes the LLM say, hey, what can I do for you? Something like that. So it triggers the LLM, makes the bot speak first, start the conversation naturally. So just to summarize, Pipecat is in one mental picture. We have this transport which handles sound and timing. We have this pipeline which handles and manages handles meaning and AI. We have RTVI which coordinates the pipeline, whether it needs to stop, run, whatever. Observer observes the pipeline and observes the pipeline task and checks the metrics and everything. So provide visibility, and then we have a pipeline task which takes care, holds the state and metrics. So you can see Pipecat mirrors how human can like hear, think, speak, interrupt, respond. And just one final mental model you can think of it as like a transport aiortc moves the sound, where detects speech, turn analyze detects turn detection. This is all part of transport. Then in the pipeline we have like a TTS, LLM, and STD, speech to text, audio intelligence audio, and RTVI in the starting, which controls the AI behavior. So this is all for two pieces like transport and pipeline. So in one sentence, like a pipeline lets you build human-like voice conversation by combining real-time audio transport with intelligent interruptible AI pipelines. So this is one example. Like if you go to Pipecat examples quick start, you will get this example, and I have uh, I have this example right over here. So let's get right into it. So we have a lot of imports. So in the starting, if you see, we are loading all the models and imports. Then we have this local smart turn analyzer as the analyzer which we are loading. It will take some time to load. That's why we have this log statements. When it is loaded, then we have logging that information and also loading the WAD model. So turn analyzer and WAD model, and then we have different analyzer, run frame, and things related to pipeline. So we are loading all the imports. Then we have two main function, run bot and bot, and we have this we are calling the main method at the bottom. So now as a part of Pipecat pipeline, when main method is run, then bot function will start running with some arguments. Now runner arguments, whatever we get, what we are doing is we are in turn passing it into the run bot function, like this runner arguments. We are passing it into the run bot method, and we are creating the transport. So this create transport is over here in the pipelet runner utils. We are putting this method, and we are passing the runner arguments and transport parameters. So transport parameters is nothing but if we are using aiortc library, then we have this WebRTC. Otherwise, if using daily, daily is a service provided by like creators of Pipecat. So this is also WebRTC based. So we can use that as well. But in case you don't want to, you have this aiortc library, and you can load the turn analyzer and WAD. So as I stated, WAD and turn analyzer, these are part of transport. So we initialize that, give those parameter and audio in enabled, audio out enabled, and this transport is then sent to the create transport, and the transport is then sent to the run bot. So on this transport that we had over here, I will minimize this bot. Okay. So first of all, before getting started any of this, just see this pipeline. In the slide we have I have showcased the pipeline. So we have this transport.input, transport.output, then we have STT, LLM, TTS, all of that, and then we had RTVI and the context aggregator, which I will talk about in a minute. So transport that we have sent at the top, it is used in the pipeline, and also on client connected and on client disconnected, we are making sure that whatever we want to run, like for example, when the client is connected, we want to send LLM, like you can say hello and introduce yourself. So we send that information and then send the LLM run frame event. And one client is disconnected, then we are just canceling that task. We are canceling that pipeline task. So now this task is something like as I stated, like this pipeline. We have created the pipeline. Then we have this pipeline task. We are passing the pipeline and some parameters. Like these are the parameters related to the enabling the metrics and all of that. And this is the observer that we are passing. So pipeline task, metrics, and the observer. We are initializing the RTVI observer, so that in case human is speaking midway, then RTVI observer takes care of that. um, and We have this task, and then we are creating the runner, pipeline runner, giving runner argument dot handles second, and runner dot run task. So this is something we did. Now coming to the STT and TTS, so it is like we are using some different models. We can use any speech to text model. So here we have this deepgram STT service which we can import and then give the API key, and then text to speech we are using Cartesia, and we can use some their API key and initialize that model. Then LLM, whatever you want to use, like here we have OpenAI LLM service, Pipecat, and allows other services to use, so you can use any other service as well. So this is STT, TTS, RTT, and then RTVI. We have this RTVI processor which we have initialized. And then coming to messages, now our voice AI should also understand the history. Like it should not start from the scratch. It needs to understand what all the conversation has happened, right? So we are creating one role and system, whether by system or user. So like we are giving some prompt like role system, you are a friendly AI assistant, and respond naturally, keep your answer conversational, like that. These are all the messages, and these messages are by which we create this context, and then this is the context aggregator. So in between, like whatever user context we are using that, and then later on whatever assistant spoke, we are sending that information. So yeah, so this is the one initial example by which we created the using Pipecat pipeline. We created this simple voice AI agent. So just to recap, uh, we have this uh, uh, Pipecat pipeline which takes care of what the AI is doing, what is the behavior of the AI, and aiortc takes care of the audio, like moves the audio, and Pipecat pipeline decides what to do with the audio. So that's about today. Thank you for watching. If you like the video, please do like, comment, share, and subscribe. Thank you.